And excitement. So I'm Kevin Hare from Waterloo, and is going to talk on uniform random walks.
Okay, so to begin with, all of this stuff is joint work with Wisdom McKay, but there's actually more people involved in this project. This was one of the more bizarre joint supervisions I've done. I was in Prague supervising a Waterloo student jointly with John, who was in Australia at the time. So they spent 2 months in Australia. By the time they came back to Waterloo, I had actually come back to Waterloo. And Gislen was one of the students, and Corey was sitting up back there as the other student. So they both had a great time in Australia, and both got papers out of the USRA. So it was a great success. So what we're going to do is we're going to consider short random walks of n steps in d dimensions. The normal analogy you always hear for random walk in dimension 1 is a drunk walking up and down the street trying to find his house. In dimension 2 is a drunk walking around the city trying to find his house. We're talking about short random walks. So we're thinking of a very, very sleepy drunk who's going to wander around the city and very quickly fall asleep on whatever park bench he or she finds. So as an example, I'm going to give a few examples. So think of a random walk, 3 steps. The largest distance you could possibly get is distance 3 from the origin, and that's if you go the exact same direction every time. You might have shorter distances, you might actually end up very close to the origin, but there's sort of a nice probability distribution of where you might end up after a short number of walks. And for convenience, we actually let nu be the dimension over 2, so we're going to look at even dimensions, -1. And then we're going to let this Pn of nu x be the probability distance function that after n steps, you will end at distance x from the origin. And if you've got a probability distance function, you can look at moments. So we'll look at the s moment of this probability density function, and we'll call this Wn. And there's a number of results that are already known about these probability density functions. For example, for non-negative integers k, we can explicitly write down what this probability density function is. And there's a rather interesting way you can compute these, in that you can explicitly write down a matrix, and then you take the nth power of this matrix and sum up a row, and that'll give you the kth term. So you sum up the kth row of the nth power, and that'll give you the term. And John had actually asked about drawing matrices in the first talk. I'm going to do that a bit later, but I should at least give you an idea of what these matrices are. Anytime mathematicians see a matrix and see numbers, they start looking for patterns. Doesn't take a lot of looking at these numbers to realize they're all squares. So you say, well, what happens if you actually look at the square root? The first row, all the square roots is 1, then it's 1, 1, then it's 1, 2, 1, then it's 1, 3, 3, 1, 1, 4, 6, 4, 1. That's Pascal's triangle. So all these entries are the square of Pascal's triangle, which, conveniently enough, since they're all based on very combinatorial things, they're all integers. I'm looking at the first one instead. Instead of looking at A0, I'm going to look at the A1 matrix. Again, all these things appear to be integers. There is a bit of structure. You could probably put these things into the online integer sequence, and it just pops out that these are the Mariana numbers, and hence they're integers. Based on 2 data points, we might conjecture they're integers. Unfortunately, that's not true. We get to the next one, A2, we've got a bunch of 3s in the denominator. And I'll talk a bit more later on about where these 3s occur, because it's actually sort of open. We know visually where they occur and that something's going on and there's a lot of structure, but we don't actually know what's going on. So they're not integers, but it was proved that every single one of these integers is either an integer or is an integer over 3. So it's in 1/3 the integers. So we're going to define R nu is the minimal sort of denominator so that all these matrix entries are in 1 over R times Z. So R0 and R1, because everything was integers, they're both going to be 1. R2, because everything was in 1/3 the integers, is going to be 3. it's not immediately clear this is even well defined. We could possibly have denominators going off to infinity as you go lower and lower this infinite matrix. Turns out they are actually well defined and they're always finite. So 2 results that we managed to show. First of all, we have an upper bound for it, 2 nu minus 1 factorial over nu factorial. If the R nu divides it, it's definitely finite. And in the other direction, we have something that actually divides it. So we have good bounds on where it lies. And we're actually conjecture that it's this second one in all cases. We're just not able to sort of tighten this up and prove this result. We do have a lot of experimental data for this conjecture. So I should give some indication of a sketch of a proof of how this works. So all these matrix entries look like this. I want to claim that all these entries, the smallest denominator I can have is that. So I multiply by what I think the denominator is. Those should all be integers. So I look at this object times this object. I'm hoping it's an integer. And I do a very careful analysis on primes. They say any prime in the bottom has to occur. If it occurs to a certain number of powers, it's going to occur at least that often in the top, possibly more. So you just do a very careful analysis on the primes dividing the denominator and the numerator to show that this is an integer. That's a very quick sketch of something that was a lot more detailed and a lot more annoying to do. In the other direction, I want to show that I have a lower bound for it. And again, I looked at this value, and you can really carefully choose the k and j. And with some careful uses of the Chinese remainder theorem, you can actually get this 2 nu minus 1 choose nu in the denominator. And factors of those that are not in the numerator. So that gives you upper bounds and lower bounds. It's not tight, but it's something. So I said R1 and R0 were both 1, R2 is 3. We can actually explicitly choose or prove R3 and R4 using a bit more detailed analysis. And these numbers here, the 5 choose 3 and 7 choose 4, match our conjecture exactly, which is partly where the conjecture was coming from. So as a sort of brief heuristic of how this is going on, we have a bunch of cases. We can explicitly just say, take the second term equal to 0, 1, or 2, and look at what the k terms are, and look at these things, and hope. We want to try to show that 10's in the denominator, so I want to show that I don't get any, I multiplied by this 5 choose 3, and I want to show that these things are always integers. Well, this thing here, either k is even or k plus 3 is even. So that's going to be an integer. Either k is even, in which case k and k plus 2, both of them have even, so we get another, it's an integer, or k is odd, and we do the same sort of analysis. One of these is divisible by 4, and they're both even, so we get that that's even. So we can get the first few cases out of the way. The next case is, it's a bit messier, but you do it for generic j, and then you write it in 2 different ways, use some Chinese remainder stuff, and do some case analysis, and you can still get it that this thing has to be an integer. So there's, computationally, this is easy to check. For any particular k, j, or b, you can just explicitly work out what the term is, and sure enough, check that the denominator is no bigger than you expect it to be. Using some of these ideas like we did for 3 and 4, we can actually show it for all j and nu less than 15, and it holds for all k. This part here is the part I was talking about, in that there's a lot more structure going on that we really haven't explained or in any way exploited. I drew a matrix. This is not clear what it's a matrix of, but this is the matrix A2, way back here. Anytime I saw 1 over 3, I put a point in there, and anywhere it was an integer, I just left it alone. So only 3's are showing up in the denominator. There's structure there. There is clearly structure there. We don't know where. why that structure is there. We haven't actually proved it in any way, but there's clearly structure there, and if we can actually get a handle on exactly what's going on, we can probably get a better handle of how to prove these precise results instead of just having conjectures. A3, well, in A3's case, we have R3 equals 10, so there's a factor of 2, possible factor of 2 in the bottom, possible factor of 3 in the bottom. Both of these are showing up. The red are things where we've got a factor of 2 in the bottom. This very light blue is where we're getting a factor of 5 in the bottom, and occasionally these match up, normally on this diagonal where we actually get a factor of 10 in the bottom, so we're getting the R3 equals 10. This one here, you unfortunately, you really can't see. There's a really faint one here. This picture is better than the other version of that I had where you couldn't see anything on any of them. So you could see the 5, you can't see the 7, it is there, and if I altered the picture some more, I probably could get it to pop out. Here, again, we're guessing it's 2, 3 squared, and 7. We're getting some of the 3's coming out in blue here. We're getting some of the 7's coming out in green. And we actually get, like, when it's 3, it sort of looks like a Sierpinski triangle with 3 things at the base. When it's 7, it's got 7 things at the base. And when it's, where's the, I guess the other one is 2, which is, 2's the red, because I've got 2 things at the base. So stuff is going on, and conjecturally, you're looking at these things. Gisman had actually written in so that if I ever found a prime factor that shouldn't have been there, that didn't match a conjecture, I'd have big flashing lights or something. And we never got these in the first 1,000 rows. So actually at this point, I'm going to comment something my supervisor, Peter, John's brother, had told me at a conference once. No one will ever complain if you end a talk early just before lunch. So I think at that point I'm going to end it early, and we can now go take our group photo and have lunch.